A fluid mechanics project on buoyancy, and I thought it'd be cool to find out if the bomb in Finding Nemo could actually exist in real life. So I took the measurements of Marlin the shark, the tension, the bomb, and the brick, and I converted it all to my experiment to see how this would all figure out. So we do know that Marlin in the real world is 4 inches because he is a clownfish. In the movie, he is 6/8 of an inch. And in the movie, the shark is 22 inches. So you cross multiply, you're able to find out the shark is really 119 inches. So you use the same type of conversion for everything else in the movie. So now you have to find out the volume of the brick and the volume of the bomb. And that you will use our regular volume formulas to find out. So we do know that the brick is steel because it does not rust in the movie, and it's the only type of metal that doesn't really rust in salt water. So steel is 0.2904 pounds per cubic inch. So you multiply your volume by this number, 0.2904 pounds, you end up with your weight. So we convert all of our real numbers over here into our experimental conversions. The Great Barrier Reef is really 35 meters deep, and that is where the movie takes place. My experiment will be 0.3556 meters deep. So we convert everything from the real world into my experiment, and we end up with the weight could weigh 78 kilograms. And that's not really practical for my box because it will fill up the whole space, and I need something that will fill up smaller space. So then I use the buoyancy formulas to find out how much weight I really need. We know that the weight of the bomb is 136 kilograms from World War II bombs. The gamma of seawater is about 10,000 newtons per meters cubed. So we look at the free body diagram of the bomb and of the brick. Of the bomb, you have the tension is pulled down because the tension is below the bomb and it's held by the brick. You have the weight of the bomb pulled down and the buoyancy force is pulled up. So you look at the formula, you have the buoyancy force is gamma of the seawater times the volume of the bomb, which we calculated on the other page, which is subtracted by the mass times the gravity of the bomb again, which is equal to the tension force. The tension force is 754 newtons. So then we use this number, 754 newtons, to find out the weight of the brick. So the weight of the brick is equal to or greater than the tension force plus the buoyancy force. Now the buoyancy force will be the gamma seawater times the volume of this brick. Now the weight can be greater than or equal to, but it cannot be less than, because if it's less than, then the brick will float up. So you really want this to be greater than. You have the mass of the weight will now equal 107 kilograms. So my experiment, it will be 1 kilogram, which is a lot more practical. So if you look at my experiment over here, we have the weight down here, which I have 50 pounds, which is less than 78 kilograms, so it works well in the experiment. We have the tension of about 3.5 inches, and the diameter of this bomb is 10 inches. As you can see, this experiment actually does work, and the only reason why this is higher than it is in Nemo is because my tension is not from the ground, it's a couple of inches higher because of my weight.